Welcome to this week's Pass the FE Exam video. In this week's episode, we're going to determine reactions at supports for beams and frames. In this scenario, we'll analyze a beam supported by a pin at A and a roller at B, carrying various loads. This problem was created and solved by mechatronical engineer Shante Thunderspay and is brought to you by PPI, a leader in engineering exam prep for the FE and PE exams since 1975.
PPI provides expert prep courses and study resources designed to help you pass the FE exam the first time. PPI's live online courses include hours of lectures, problem-solving demonstrations, exam strategy sessions, office hours, and a passing guarantee. When you take a live online course, PPI guarantees you will pass, or you can take the on-demand course for free. With study guides, practice exams, and more, the PPI Learning Hub offers digital practice and review that you can take with you anywhere you have a device so that you can prepare during the times most convenient for you. Check out PPI today at ppi2pass.com to see all the options available for FE exam prep. Let's dive in.
In this question, we are given a diagram showing a beam with a series of external forces acting on it. Specifically, a concentrated 6 kN load at its right end and a distributed load on its left end, reaching a maximum force of 2 kN per meter. The beam is supported by a pin at A and a roller at B, and the question asks us to determine the reactions at these supports due to the external loading conditions. To kickstart the problem, we must first draw a free body diagram of our beam. To start off, we can include our two support reactions, AY and BY. Since A is a pin support, you might be tempted to include an extra reaction force in the X direction, but this component would ultimately be zero, since we have no other forces acting in this direction. Continuing to the next force, we can also add the concentrated 6 kN load at the beam's far right end. And now for the more complex part of the question. To work with the distributed loads acting on the beam, we first convert them to equivalent point loads. These individual resultant forces must have the same external effect on the beam as the original distributed load has. We can start off by inspecting the uniformly varying load on the far left end of the beam. And as we can see, this distributed loading steadily increases from 0 at the left end to 2 kN per meter. To find the equivalent load of this section, we can compute the area under the triangular curve. Since the area of a triangle is commonly known to be a half base times height, the area or equivalent force is given by a half multiplied by 1 meters times 2 kN meter, resulting in a point load of 1 kN. But now you may ask, where exactly does this force act? Well, it acts at the centroid of the triangle, in other cases also referred to as its center of mass or balance point. And the centroid of a triangle can be found by drawing each of the three mediums, which connect the vertices of the triangle to the midpoints of the opposite sides. And although calculating these distances may sound a bit intimidating, we're lucky that in this case we are working with a right triangle, meaning the centroid will always be located at a distance of 2/3 the length of the base from the angle opposite the right angle. So the equivalent 1 kN point force would act at a distance of 2/3 meters from the left side of the beam. We can now move on to the rectangular distributed load, and to compute its equivalent point load, a similar procedure is followed as before. The equivalent load is found by calculating the area below the rectangular curve, given by base times height, and the load is then found to be 4 kN. Since we're working with a symmetric shape, the equivalent point will simply be working in at the center of the rectangle, which is 2 meters from the left of the beam. And this final equivalent force allows us to complete our free body diagram so that we can start calculating the reaction forces at supports A and B. And as long as your free body diagram is correct, you should find this to be a pretty straightforward process. We start off with a simple force balance in the y direction. Since this beam is static, we know that the sum of the forces in the y direction must equal 0. By choosing upwards as the positive direction, we have that force AY plus by -1, -4, -6 is equal to 0. And when we simplify this, we end up with force Ay plus by -11 is equal to 0. Now, since we still have two unknowns, we need one more equation to solve for these variables. And this equation can be found by taking a moment balance about either point A or point B. In this case, I'll be using point A. By taking anti-clockwise as the positive moment direction, we can start writing our equation by taking careful note of the distance of each force from point A. Since the 1 kilonewton force is 1/3 of a meter from A and causes an anti-clockwise moment about this point, we add 1 times 1/3 to our equation. Beyond this, the 4 kilonewton force acts at a distance of 1 meter from point A and causes a clockwise moment. So 4 times 1 must be subtracted from our equation. Similarly, we complete our equation by adding force By times 2 and subtracting 6 times 3, and the resultant of these moments all equals 0. By solving equation 2, we find that reaction By is equal to 10.833 kilonewton. And finally, reaction By can now be substituted into equation 1 to find that Ay is equal to 0.167 kilonewton. And that completes our problem. By browsing the options given to us, we can see that the final answer is equal to A. I want to conclude this problem by offering some pointers. When starting a problem like this, I recommend spending majority of your time on the construction of your free body diagram. Stay mindful when finding the equivalent forces from distributed loadings, and make sure of the distances at which these forces act. When tackling more complex problems, I found that this is often the greatest source of error. Secondly, ensure that you correctly identify the support types that you are working with. This becomes especially important if you have external forces acting in the x direction. Thirdly, apply the equations of equilibrium correctly, paying attention to signs and units. I recommend choosing a convention for your positive directions and sticking to it. For example, in this question, we chose upwards and anti-clockwise as positive. By sticking to the same convention throughout your practice, you might find that you make less errors in this regard. Finally, and as always, hone your skills by practicing with different loading and beam configurations so that you can become confident in your ability.
I hope you found this week's video helpful. In upcoming videos, I'm going to answer more of your FE exam questions and run through more practice problems. Past the FE exam videos will publish weekly, so please be sure to hit that subscribe button so we can help you to pass the FE exam and set your engineering career up for success. And if you have questions or comments, put them below this video and we will respond to them. I'll see you next week on Pass the FE exam.